Imagine for a second, right, that you are just miles and miles away from civilization. Maybe you're out on a boat, you've got salt spray in the air, just endless blue horizon in every direction.
Sounds pretty ideal.
Right? Or, maybe you're deep in the wilderness, completely off the beaten path. But suddenly, you realize you urgently need to pull down a high-resolution weather model.
Oh, yeah, because out there, the weather can change in an instant.
Exactly. The barometric pressure is dropping fast, and those clouds in the distance are looking really menacing. And, the dream of seamless anywhere internet has been this tantalizing promise for a while now.
It really has.
But the physical reality of just like throwing a satellite connection in your backpack and expecting it to function flawlessly in the middle of nowhere, it's far more complicated than the marketing suggests.
Oh, massively.
Yeah.
The gap between that slick marketing promise of, internet everywhere and the actual brutal physics of operating delicate electronics in harsh environments, it's huge.
Yeah.
The idea that geography no longer dictates connectivity is super compelling, but actually establishing a stable link to a satellite that's moving at orbital speeds.
Right, while you're bouncing around.
Exactly, while you are pitching in 3-foot seas. I mean, that requires an understanding of some really serious engineering constraints.
Okay, let's unpack this.
Yeah.
Because when I think about maritime satellite internet, my mind immediately goes to traditional VSA systems.
Sure, the classics.
Yeah. I picture those massive, heavy white domes bolted to the mast of a ship, hardware that costs, tens of thousands of dollars?
At least, yeah, and requires a literal crane to install.
Exactly, a crane.
Yeah.
And it essentially needs a small power plant to keep it running.
Yeah.
So the modern promise of portable hardware is just a complete departure from that legacy.
It is. We were looking at a radical shift in form factor here. But, and this is crucial, in the world of marine electronics, the form factor completely dictates the function.
Right.
You simply cannot shrink a piece of technology without making some kind of compromise.
Which brings us to the source material for today's deep dive. We are looking at a comprehensive technical guide from Marine Data Solutions, which was authored by Marine Network architect Michael Robilio.
It's a great guide. Very thorough.
It really is. And our mission today is to completely decode the Starlink mini kit. We are going to look at the underlying architecture, the specific deployment limitations, and basically figure out whether this is actually a viable solution for remote connectivity.
Or, if there are hidden structural bottlenecks you absolutely must understand before you go relying on it in an emergency.
Right. So where do we start?
Well, understanding the hardware architecture is paramount. When we compare the new Starlink mini kit to the Starlink standard kit, the difference isn't just about size.
Okay.
It is a fundamental change in how the network is actually processed.
So with the standard kit, that relies on a distributed setup, right?
Correct.
Like you mounted the phased array antenna outside to communicate with the constellation, but that antenna routes a physical cable inside to a completely separate Wi-Fi router.
Exactly. The router handles the local network traffic, and both of those components draw their own dedicated power.
Got it.
It is really designed for a semi-permanent installation, like, a house or an RV that stays parked most of the time.
Okay, so how does the Mini change that?
What's fascinating here is how the Mini completely collapses that architecture.
Oh, wow.
Yeah. The Mini kit integrates the phased array antenna and the Wi-Fi 5 router into a single cohesive chassis. And it's roughly the size of a thick laptop.
That's incredibly small.
Right. So you aren't really installing a network anymore. You are just powering up a monolithic device.
Okay, so what actually comes in the box then?
Inside the box, you get the terminal itself, a kickstand, a pipe adapter, a flat mount, your power supply, and a 15-meter, so about 49-foot DC power cable.
It's like the difference between buying a high-end desktop computer, right, with a separate tower, a discrete graphics card, a monitor, all the cooling fans.
And all the cables everywhere, yeah.
Exactly. Versus buying a sleek, ultra-thin tablet. The standard kit is the desktop, and the Mini is the tablet.
That is a perfect analogy, and honestly, the tablet analogy highlights the exact limitation we need to discuss first.
Okay, I'm listening.
A tablet is brilliant for portability, right? But because all the heat-generating components, the processor, the battery, the screen, they're all sandwiched together in this super tight space.
Right, they get hot.
Extremely hot. It suffers from severe thermal constraints. It just cannot dissipate heat the way a desktop tower can.
Oh, I see. So packing a phased array antenna, which I imagine requires a lot of power to electronically steer its beam.
To track moving satellites. Yeah, exactly.
Right, so packing that into the exact same plastic housing as a Wi-Fi router that's handling local packet routing, that creates a massive thermal and power bottleneck.
Bingo. The physical density literally limits its processing power. The router inside the Mini simply does not have the computing overhead or the thermal headroom to handle heavy enterprise-level network traffic.
Wow. Okay, so that physical limitation completely changes what kind of boat you can actually put this on.
Oh, entirely.
Because it's so small, and it's DC-friendly, the temptation is just to toss it onto literally any vessel, right?
Yeah.
From a tiny center console to a 150-foot super yacht, and just expect flawless internet.
Yeah, but you can't do that. Michael Robilio's guide draws a very hard line regarding the ideal use cases here.
What does he recommend?
The guide specifies that the Mini is built for day boats, small center consoles, yacht tenders, and weekend cruisers. It functions best on, inland lakes, rivers, and coastal anchorages.
Okay, wait a second. I actually have to push back on this distinction a little bit.
I bet, go for it.
If the satellite is literally orbiting in low Earth orbit, right, hundreds of miles up in space, why does it care if the receiver is sitting on the deck of a 20-foot fishing boat versus a 100-foot luxury yacht?
That's a fair question.
Right. Shouldn't the signal beaming down be identical for both?
Well, the satellite overhead doesn't care about the size of your hull at all. The restriction isn't about the RF signal coming down from space. It is entirely about the throughput demand on the hardware down on the water.
Oh, I see.
We have to look at the vessel's local connectivity profile.
You mean like the sheer volume of devices trying to push data through that tiny internal router simultaneously?
Exactly. Think about the multi-user demands on a large vessel. You might have, say, 10 charter guests all expecting uninterrupted 4K video streaming.
Yeah, that's a lot of data.
Plus, the crew is running VoIP communication. The captain absolutely requires continuous, real-time weather overlays, routing updates downloaded to the navigation suite.
Right, mission-critical stuff.
And you might even have the owner conducting a high-stakes encrypted video conference at the same time.
Oh, wow. Yeah, if you push all of those simultaneous packet streams into the Starlink Mini's integrated router, it's just going to choke.
It will hit a thermal wall or a hard processing limit and just start dropping packets. One person on a tender checking a radar app is a completely different computational load than 20 people living highly connected, bandwidth-heavy lives.
Makes sense. So for a large vessel, connectivity really is mission-critical infrastructure.
It is. It requires always-on reliability and sophisticated traffic shaping. The Mini, just because of its integrated nature, is more of a casual, temporary deployment tool.
Okay, so if a single integrated unit chokes on that kind of heavy load, larger yachts must have to isolate the antenna from the local network entirely.
We're exactly right.
They must need a dedicated piece of hardware just to pull the signal down, which then feeds into some beefy enterprise-grade routing system to balance all that load.
Yeah, and that requires stepping up to the Starlink high-performance kit. That kit physically separates the heavy-duty antenna from the internal routing.
Back to the desktop model?
Precisely. Furthermore, the guide emphasizes that yachts rely on hybrid marine networks. And this means seamlessly bonding the satellite connection with local 5G cellular modems.
Oh, that's cool. So a mile offshore, the system routes traffic through the much faster, lower latency 5G network.
Yes. But then once the boat crosses into deeper water where those cell towers fade out, the router automatically shifts the load to the high-performance satellite dish.
And the users on board never even notice the transition.
Exactly. Blurring the lines between temporary mobile tools and professional-grade infrastructure, that's where users run into massive frustration. The hardware must match the network demand.
Okay, but the vessel profile isn't the only restriction, is it? Because there is a geographic limitation built into the service plans, too.
Oh, big time.
Yeah, people assume a portable dish means they can just sail anywhere in the world and fire it up. But Starlink utilizes geofencing, right? To enforce strict operational boundaries based on whatever plan you purchase.
They absolutely do. The standard roam plans, which are typically the ones paired with the Mini for RVs or coastal boats, those are strictly limited to land and territorial waters.
Because Starlink terminals have built-in GPS.
Right. They constantly report their physical coordinates back to the network.
So once that GPS module registers that you have crossed the 12 nautical mile limit marking international waters,
the network simply drops your connection. Boom, gone.
wow, just cuts you off.
Yep. To operate past that boundary, you are required to upgrade to ocean mode, which shifts the billing structure entirely.
I can imagine.
The system actively monitors your position to enforce its commercial tiers. So taking a portable dish offshore without understanding how geofencing restricts your specific data plan, that will leave you completely locked out of the network just when you need it most.
Okay, so understanding the network limitations is really only half the battle here.
Nearly half.
Let's move from the software restrictions to the physical reality of surviving the marine environment. Because the guide is incredibly detailed on the physics of a proper setup, starting with power.
Power is everything.
Right. The Mini is celebrated because it can run on DC power directly from a boat's battery bank, which bypasses the need for a bulky AC inverter.
Which is great. Running directly on DC is highly efficient. But it introduces a severe vulnerability regarding power stability.
Why is that?
Because on a marine vessel, the electrical system is highly dynamic. It's not like plugging into a wall at home.
You know, it's like trying to plug a top-of-the-line 4K smart TV into a sputtering gas-powered generator and then blaming the TV when the movie buffers.
That is exactly what it's like.
You have to feed it clean power. The Mini's internal electronics require a perfectly smooth, uninterrupted flow of electricity, right?
Yes.
So if your boat's wiring introduces any sudden drops in pressure, the data just stops flowing.
That is a perfect analogy. Let's actually trace the mechanism of a voltage drop. Say you are anchored out somewhere, right? And an automated bilge pump kicks on, or someone flushes an electric marine head.
Okay.
Those heavy DC motors require a massive instantaneous surge of amperage just to start spinning.
Right. They pull a ton of juice.
Exactly. And if the boat's wiring isn't robustly gauged or the battery bank is even slightly depleted, that sudden demand for amperage causes the overall voltage across the entire electrical circuit to plunge.
Even just for a fraction of a second.
Just for a fraction of a second. But the Starlink Mini relies on internal capacitors to smooth out minor power fluctuations. They cannot bridge a deep voltage sag like that.
So what happens?
If the voltage drops below the operating threshold, the processor basically starves and forces a hard reboot.
Oh, man. So the user looks at their phone, they see the Wi-Fi drop, and they immediately assume Starlink is having a satellite outage or that the dish is broken.
Right, they blame Elon.
Yeah. But the actual culprit is a localized power failure caused by the boat's own infrastructure.
Exactly. And this specific issue is really exacerbated by that 15-meter DC cable included in the kit.
How so?
Well, pushing low-voltage DC power over 49 feet of wire introduces significant resistance.
Ah, of course. The longer the wire, the more voltage is lost simply to heat generation along the cable run.
Precisely. So if you start with exactly 12 volts at the battery, by the time the electricity actually travels through 49 feet of standard gauge wire, it might reach the Starlink dish at like 11 volts or less.
Which leaves absolute...
You are already operating on the ragged edge of the device's minimum power requirement.
Wow, okay. We also need to elevate the conversation around placement, I think.
Yes, placement is huge.
The instructions will just tell you to place the dish under an open sky, which, you know, is obvious enough. You obviously can't put a satellite receiver under a heavy fiberglass hardtop.
Right.
But on a boat, you have to contend with radar shadowing and active radio frequency interference.
If we connect this to the bigger picture of marine electronics, a vessel's mast is prime real estate. Space is incredibly tight up there.
Always.
So the temptation is to just mount the portable Starlink Mini right next to the existing marine radar dome. It just seems convenient.
But the guide explicitly warns against this, right? And the physics behind it are really critical.
Super critical. Marine radar systems operate by emitting intense, high-power pulses of microwave energy.
Okay.
And Starlink dishes utilize low-noise amplifiers, or LNAs, at the very front end of their receiving circuitry. This is so they can detect incredibly faint signals coming all the way from orbit.
Which means those amplifiers must be extremely delicate.
Extremely. So if you mount the Starlink Mini in the same horizontal plane as, say, a 4-kilowatt or a 12-kilowatt open-array radar.
Oh, no. Every time that radar antenna sweeps past the dish, it blasts those delicate amplifiers with a concentrated beam of microwave radiation.
Exactly. The radar pulse will completely saturate the Starlink receiver, causing massive packet loss and latency spikes. But more critically, prolonged exposure to that kind of intense RF energy can permanently burn out the phase shifters within the Starlink panel.
You essentially fry the internal components by physically cooking them with your own navigation equipment. That's wild.
Yep, you're cooking it. The Mini absolutely must be mounted significantly above or below the radar beam's horizontal path to survive.
And physical survival also extends to the cabling too, doesn't it?
Oh, yeah.
Because a temporary setup often means cables are just draped loosely across the deck or over bulkheads.
Which is a disaster waiting to happen. A loose cable resting against a sharp fiberglass edge might seem completely harmless while you're sitting at the dock.
Right.
But when that boat gets underway, high-frequency vibration from the engines translates straight through the hull.
So 3 hours of continuous vibration at cruising speed
Will cause that fiberglass edge to act like a literal saw blade. It will cut right through the cable's external insulation.
And once the insulation is compromised, salt water is introduced to the copper wiring.
And salt water and electricity do not mix.
No, they don't. Salt water doesn't just cause a localized short circuit either, right?
Mm-hmm.
Through capillary action, the water can actually wick up the inside of the cable jacket.
Yes. It pushes corrosion straight into the connectors, and it can potentially ruin the Starlink hardware itself.
The compounding variables of voltage drop, RF interference, and physical abrasion. It really demonstrates why temporary ad hoc setups in marine environments frequently fail.
They almost always fail eventually.
You know, Marine Data Solutions actually includes a very revealing pro tip in this guide. For customers located in South Florida, they offer to apply 10% of the Starlink Mini equipment price toward professional installation.
I saw that, and that detail speaks volumes.
Right.
The manufacturer heavily markets this device as a consumer-friendly, plug-and-play solution. But a marine network architect recognizes that proper integration into a DC electrical system,
Calculating wire gauge for voltage drop, installing proper inline fusing,
and analyzing the radar beam path for safe mounting. All of that requires professional expertise.
the inherent capability of the hardware means literally nothing if the installation parameters aren't respected.
Exactly. And the guide also really emphasizes testing protocols. Before a vessel even unties from the dock, the network must be stress tested.
Because you cannot wait until you are 10 miles offshore, actively trying to download a weather overlay to avoid a squall, to discover that your improvised 12-volt adapter isn't delivering enough amperage to maintain the satellite lock.
That is the worst possible time to find out. You must load test the local network, confirm the connection speeds, and actually verify that the device remains stable while the boat's other high-draw DC systems are running. Turn on the bilge pump, flush the head, test it all.
So what does this all mean for you, the listener? When we synthesize all these technical realities outlined in Michael Robilio's guide, the Starlink Mini Kit remains a marvel of miniaturization.
Oh, without a doubt.
Compressing a phased array tracking antenna and a local routing network into a chassis that fits in a backpack. It is an undeniable engineering achievement.
It's incredible. But it is a highly specialized tool engineered for a very specific operating envelope.
Right.
It thrives in temporary deployments on small coastal vessels and as an emergency fallback system where the power supply and mounting location can be tightly controlled.
Expecting that single integrated unit to perform like a distributed enterprise-grade marine network is just a fundamental misunderstanding of physics.
Exactly.
The thermal constraints, the processing bottlenecks, and the strict geofencing parameters mean it simply cannot replace the infrastructure required for heavy offshore use.
Success with this technology requires an honest assessment of your specific environment. Matching the hardware's thermal and computational limits to your actual use case is honestly the only way to avoid catastrophic failures out in the field.
The ultimate takeaway here is that convenience comes with strict architectural compromises. Whether you are outfitting a center console, wiring up an overland vehicle, or just looking for an off-grid backup, ignoring the physics of power delivery and RF interference will leave you disconnected.
But as the components continue to shrink and the efficiency of phased array technology improves, we are definitely going to see these limitations pushed further.
Oh, absolutely.
The barrier to bringing high bandwidth data into harsh environments is steadily collapsing.
Which leaves us with a lingering question for you to consider. If the engineering continues to advance, and the physical constraints of power and thermal management are eventually solved, making it effortlessly easy to drop a gigabit connection into the absolute most remote, untouched corners of the globe, what actually happens to the concept of being off the grid?
Wow.
Right? The grid is no longer a physical infrastructure of utility poles and fiber optic cables that you physically travel away from.
Yeah.
It is rapidly becoming an invisible, omnipresent canopy covering the entire planet.
It's everywhere.
In a few years, as this technology becomes completely ubiquitous, will we have to artificially force ourselves to leave the hardware behind? because the ability to simply get away from it all may no longer naturally exist.